Hi, this is Jason Baker, and welcome to our Week 13 lecture, where we will cover orchestration. Orchestration is an important topic because it brings together a number of different concepts that were covered in this class. And when we deploy infrastructure in the real world, typically we're using some sort of orchestration environment. And that orchestration environment is used to manage the deployment and the ongoing maintenance of our infrastructure services. In this week's lecture, we'll start by covering service discovery because service discovery is a really important mechanism which enables orchestration. And we'll look at a couple different solutions and one solution in particular, a solution called Consul. And then most of the lecture, I'll focus on container orchestration. And we'll look at a number of different solutions in the marketplace to enable the orchestration of Docker containers. We'll look at the AWS ECS solution, and we'll look at Kubernetes, and then we'll spend a lot of time looking at the Docker Swarm orchestration platform. And I'll also provide some hands-on demonstration of how you would work with a Docker Swarm cluster. Okay, let's dive into the material. So what is service discovery? Well, service discovery is a process which one service will use to figure out where another service is located. And so when you think about any sort of platform or infrastructure environment that you're deploying, you're typically deploying a number of different services. You might have web servers, you might have application servers, database servers, caching servers, and so on. And when you launch these different services, you are typically wiring up these services to communicate with one another. For example, your web application might need to know the location of your database server so that the web application can, talk to the database and make updates to database tables and insert new records and so on. Well, in order to wire these services together, you need to know the different service endpoints. You might need to have credentials, to talk to something like a database. How does one service know how to communicate with another service? And that goes to the heart of this service discovery process. Uh, and there's what you'll find is that there's a couple different ways that we can configure services to communicate with other services. Now, a modern microservices architecture is heavily dependent on the service discovery process because typically when you're building a microservices platform, you're you're instantiating dozens, potentially hundreds of different services. And these services need to be able to route requests uh, uh, to other services based upon availability. You'll have different services that are running in an active sort of configuration. You'll have other services which are running in active passive configuration. And so services need to be able to figure out, uh, which other services are active and need to understand how to route requests to those active services. You might need to be able to support some sort of service versioning, especially when deploying new services in a microservices architecture, because oftentimes you are using some sort of canary deployment or rolling update process. So while you're rolling out new service updates, there has to be some sort of service discovery process in place so that the legacy services can communicate with the new services that are being created. And then finally, you might need to adjust service requests based upon topology changes in your infrastructure environment. You might have container hosts that are failing unexpectedly. You might have an auto scaling group in place, which is automatically scaling your infrastructure. And as your infrastructure scales, you're you're adding new services or expanding the count of existing services. So as those new services start up, they need to be able to find other services within that infrastructure environment. Well, there's there's a couple different methods that we traditionally use to to discover services within an environment. Traditionally, this is sort of before the cloud era, we would oftentimes hard code service locations into our services. And that was because our infrastructure just didn't change all that often. You can imagine like a traditional on-premise data center where you'd have like one service running on each physical server. You weren't like adding or removing physical servers all that often. You might do it on a monthly or quarterly basis. And when you were adding new servers and services, you could, easily just hard code in the other service endpoints, right? Because you just weren't changing the infrastructure all that often. Well, so another method we can use for service discovery is to use the output from some sort of infrastructure definition tool and use that output to determine service location. So for example, you could use a tool like Ansible to deploy a web server and a database server and a caching server and so on into your environment. And because Ansible is launching these different services and creating these services, it knows where those services are located. And so it can provide the web server with the location of the database server because it created the database service. Well, so that process, it can be really useful and helpful, but it typically only works during some sort of bootstrapping process. So if you're launching an environment for the first time and you're building a web server and a database server, it's easy for this tooling to kind of wire those services together. But if they're running in something like a cloud platform, and the services and the infrastructure is more dynamic. So, the EC2 instance, which is supporting the database server, if that fails, it goes away and is then automatically replaced by something like an auto scaling group. Then the database server location might change, and so there would be no way to communicate that new service endpoint back to the web server, unless you're like rerunning Ansible or some other tool, sort of continuously and trying to like resynchronize the service configuration information in the environment. So the third method is to use some sort of dedicated service discovery platform. And this is really the most modern way of dealing with the service discovery. And what a service discovery platform does is it provides uh, this sort of centralized directory or database that stores the service endpoints for all the different services running in your environment. In this example, we have a couple different services. So we have this catalog API service. And when that catalog API service starts, it will register its endpoint with the service discovery platform. And when the orders API starts, it also registers its endpoint. And then finally, when the UI service starts, it might register its endpoint with the service discovery platform, but it can also request the endpoints for the orders API and catalog API. So that the service discovery, this platform is also like this directory service. So services can use the service discovery platform to find the location of other services within the environment. And if the catalog API service fails and it starts in some other location, then it can register its new endpoint with the service discovery platform. And the service discovery platform then can notify other services that the catalog API endpoint has changed. When we were configuring service discovery in our traditional environments, we were using services like domain name services, where we could map the IP address of a system to a domain name. And the benefit of that is that you could configure a service to point to a domain name, and you didn't have to worry about the sort of the IP address associated with that domain name. The domain name could point to a different IP address if the service was launched on a new machine. The problem with DNS is that while it's sort of dynamic, it's really not dynamic enough, especially for sort of modern cloud applications. It's also not really designed to handle dynamic infrastructure changes. For example, your traditional DNS system doesn't know if a server has failed. So if a server fails, the DNS server will continue to route requests to it because it has no understanding of the health of the server. Another method that we might use, particularly on Unix type systems or Linux systems, is to set up a mapping between service port numbers and service names in something like the etc services file. This is kind of similar to DNS, but at a service port level. And then finally, a traditional method for storing service information was to store that information in some sort of distributed file system or database. And oftentimes we would call these lock servers. What these lock servers do is they basically allow a group of nodes to synchronize activities and agree on shared information. So you could imagine a scenario where you might have you might have to store some critical service configuration information in your environment. You don't want to store this information on just one server because that wouldn't be very resilient. If your single service directory server failed, then that would have probably a pretty catastrophic impact on your environment because services would no longer be able to find one another, especially if there were infrastructure topology changes. So our preference would be to store that service configuration information on multiple servers for redundancy and reliability. In this example, I have three different servers, and each server is storing a key value pair. In this case, the key is X and the value is 2. And what we want is we need to be able to synchronize these key values across all three of these systems. And we need to ensure that these systems are all agreeing on the same value because you want to avoid a situation where you're querying your service discovery platform and you're querying it for the value of X, and one of the servers thinks that the value of X is 2 and the other one thinks the value of X is 3, and you're getting inconsistent results back. So the idea behind a lock server mechanism is that you can take a value or a set of values and you can consistently store those values across multiple systems and keep those values all synchronized. And so that anytime you query these systems, the systems are all returning the same value. And this it turns out that this is actually a very challenging problem. This idea of trying to figure out how do we synchronize the value of this key pair across multiple systems. You could imagine a situation where we have our three servers again, and let's say that two of our servers go offline, and then we only have one of the three servers which is actually available, and we decide that we're going to update the value of our X key and set that to 3. Well, now we have a situation where if these other two servers come back online, two of the servers have the value where X equals 2, and one of the servers thinks that the value of X is equal to 3. And that could be a real problem. I mean, imagine that X isn't holding the value of 3. Maybe X is holding the service endpoint for the database service. And in this case, one of the servers and the lock servers thinks that the database service is located at one endpoint, and the other two, service discovery servers thinks that the database service is located at a different location. And that would cause some real problems in our environment is if we have, we're launching new web application servers and they're trying to figure out where the database server is located. Some of those web application servers would likely fail because they couldn't establish a database connection. So how do we solve this problem? Well, one of the common ways to solve this problem is to use what's called the RAFT algorithm, and so this is a really common algorithm that's used, especially when we're trying to build clusters. And with the RAFT algorithm, essentially what's happening is you have a group of nodes, and this group of nodes will elect a leader node, and the leader node kind of controls what values are going to be stored within that cluster of nodes, and it controls many of the synchronization processes. If the leader node fails for some reason, then the remaining nodes will elect a new leader. As long as there is a quorum, or at least a majority of nodes present within the cluster. Information then is also shared and stored across all of the nodes in the cluster. If you want to see a really interesting demo of the RAFT algorithm, I have a URL at the bottom of this slide. And I strongly recommend watching this demo, because it gives you a good visual sort of animation of how this RAFT algorithm works, and how it can distribute information across the cluster, how it deals with topology changes like the failure of a cluster node. So we can use things like the RAFT algorithm to store data, to store service configuration information across a set of servers, a set of distributed servers, and that then can form the heart of our service discovery platform. As services come online, they can query the service discovery platform, and and make requests for the location of other services within the environment. And because the service discovery platform is using something like the RAFT algorithm, the service information that's stored within that platform is stored in a very consistent, highly available, and resilient manner. There's a number of different service discovery platforms that you'll encounter in the marketplace today, and I'll cover a couple of them here just so that you're familiar with these services, because you'll encounter them from time to time. The first one is a platform called Apache Zookeeper. And Zookeeper was originally started as a project at Yahoo, and then became part of the Apache Foundation. And it's also a sub-project of, it was started as a sub-project of Hadoop, but is now considered a top-level project. So if you are building out a Hadoop cluster, then typically a Zookeeper will be a part of that. And Zookeeper is providing that service discovery mechanism within the Hadoop cluster. So as cluster nodes start up or as they shut down, then Zookeeper is keeping track of those resources. Another service discovery platform is etcd, and etcd is a distributed key value store that you can use to store shared configuration data for a platform. It's written in the Go programming language, and it's maintained by a group called CoreOS. And this is an open source service discovery service. It's commonly used in container-based orchestration platforms, such as Kubernetes. The third service discovery platform that I want to talk about, and I'll focus more time on this one, is a platform called Consul. And Consul is designed by HashiCorp. Now, you've already encountered HashiCorp several times in this course. We've looked at tools like Packer, we've talked about Terraform, and other tools. So this is a service discovery platform which they built, and it's a client server platform. You have both Consul agents, which will run on each one of your servers in your environment. And then you'll have Consul servers, and Consul servers are storing your service configuration information. So your Consul servers are, sort of like your distributed databases, which are storing those values, those service configuration values. The servers in Consul actually use that RAFT algorithm, so that's what they use to maintain, consistent data across all of the Consul servers. And then the Consul agents that are running on all of your different like application and database servers in your environment, those Consul agents then are querying the Consul servers for that service discovery information. I mentioned that the Consul servers, it can be used to store information. They can serve as a distributed key value store, similar to something like like Redis. What's also interesting about Consul is that Consul supports health checks, and so the Consul can monitor the health of the services within the environment, and as it sees different services failing, it can then update the service discovery information to route requests around sort of unhealthy hosts within an environment. So that's a really interesting feature that Consul provides. In terms of accessing and querying service information within Consul, you can use both an HTTP RESTful interface, or you can also query Consul service discovery information using DNS, which is very interesting because sometimes you have applications which, and these are more legacy type applications, which don't know how to talk to an HTTP RESTful interface. But most any application can make a DNS request, some sort of name service request. And so Consul provides that DNS interface to support legacy applications. I mentioned that the Consul architecture is this client server based architecture. Every node within your environment runs a Consul agent, and the Consul agent is able to communicate with the Consul servers. The Consul agent is also monitoring the health of services that are running on the node, and that agent will then report that service health information to the Consul servers. The Consul servers then will store configuration information, and they'll replicate that information across multiple servers and ensure that information is stored consistently. The servers use the RAFT algorithm, so they'll form a cluster, they'll elect a leader, and typically you'll run 3 to 5 servers, Consul servers, in an environment, and you do that because you want to be able to support high availability. So if one of your Consul servers fails, then you have other servers that are still up and running, and that can service the service discovery requests. Here's a Here's a diagram showing you the basic console architecture. In this case, we have like two data centers, which are modeled here. One data center has console servers in it, and it also has other servers that are running the console client. Now, um, Consul, when it stores the information, it will store information consistently across all of the nodes in the console cluster. It'll replicate, synchronize that information, and all of the data reads that are made to console servers are strongly consistent, meaning that if you read the value of a key or you get like a service configuration endpoint value, that value is going to be the same on all of the servers in the console cluster. And console, because it values strong consistency, it will actually sacrifice availability for consistency in the case where there's some sort of console server failure or network partition. So remember back when I was talking about lock servers and the RAFT algorithm, there was a situation where I showed you three servers and two of the servers had failed and one of the servers was updated where X was no longer equal to 2, X was now equal to 3. And that was a real problem. Well, the RAFT algorithm wouldn't allow that. And because Consul is using the RAFT algorithm, um, what Consul would do in this case is if two of the three servers were unavailable, there would no longer be a quorum, a majority of servers available. And Consul then would only allow reads to be made. It would no longer allow you to make updates to keys within the console cluster. And that's because there is no quorum available in the cluster. So availability is sacrificed for consistency in this sort of situation. And this sort of harkens back to the CAP theorem that I talked about earlier in the course. Remember where we had, we in any sort of distributed database, um, we had to make a choice between availability, consistency, and partition tolerance. We couldn't have all three of those characteristics simultaneously. And this is a situation where, we said that data consistency is more important than availability. So if we don't have a quorum of nodes available, then we'll no longer allow users to write data to the system uh, because we want to ensure that that data is going to be consistent across all the nodes in the cluster. When so each node in an environment running the console service discovery platform is running a console agent. And when we start up a service on a server, we'll use the console agent to register that service with the console servers. And there's a couple different ways to do that. We could set up a JSON file that is, storing key value data. So like when our web server starts, we'll set up this this JSON file, which is telling console, you know, it's giving it some information about our web server. Maybe this is something that a configuration management tool like Ansible has put in place for us. That'd be a really common, way to do that. And then once we've registered our services with Consul, then other services in the environment can query Consul to find our new service. So, for example, if you look back at this JSON configuration file, we're registering a new service called web server. We're giving it a tag called Nginx, and we are registering it on port 80. Another service in our environment then can create a DNS request, and it can ask uh, and it can query Consul for this service called the web server service, and Consul would respond back with the service endpoint or port or whatever it has been configured for that particular service. A service can also query Consul using an HTTP endpoint, so it can use this RESTful endpoint to learn some service information as well. I mentioned that Consul can act as a key value store, similar to something like Redis. And it's really easy. So if I want to, um, you know, I can insert values into the Consul store by using the Consul agent. In this case, we're using Consul as like a command line. Um, we're using it as like a command. So Consul, we're telling it to put a value in the key value store, and here is the key, and the value is 1. We can delete that value from the store. We can also get that key from the store using the Consul agent. So it's very common to use Consul as both the service discovery mechanism and to use it as a general key value store.